Good. You see the notes? Whiteboard? Good. So 1D wave equation. So let's start with writing down the wave equation in its strong form. And then we pretty much use the same setup like we had when we looked at the spectral element method. And then we can basically compare this low order solution with a finite volume approach with a higher order solution of the spectral element approach. So let us quickly put down the 1D wave equation. And now you have seen that quite a bit. So let me just put it down. We have density rho times the acceleration. S here is displacement. And then we have these partial derivatives with the shear moduli times the strain. So this is the equation we're going to solve. It's the homogeneous 1D wave equation. We don't use a forcing term, but rather just start from an initial condition. So we have displacement S, which depends on position and time, then density, which is a function of position, and so is the shear modulus, or the shear moduli mu. So we will set an initial condition. Where we just start from an initial displacement. So the displacement at time 0 is going to be some function of position. That's just the initial condition. And the boundary conditions will be the same like in the spectral element example. So we have the Dirichlet boundary. Oops. Where we fix the displacement. So domain goes from 0 to L. And then we have the position at L and at 0. We're going to fix them to be 0. So this would be the Dirichlet boundary. And or the Newman boundary where we fix the derivatives at these points. So again, this could be, for example, a function, a boundary function that we would define for each time if we want. Here we just set this to 0 as well, just to make it a simple example. The same for the boundary at point 0. Could just be again a boundary function, but we just put this to 0 as well. So this is the Newman boundary condition. Right, so what is the first approach for the finite volume method? First step is going to be what?
Write the integral form of the equation.
Right, so what we need is the integral form. And so first let me show you how the approach works, for example, in the books from Randall Levesque or from Heiner Eagle, where we look at first order PDEs. So they start like with this first way of looking at it to solve it. So for the finite volume method, one way to solve the wave equation is to cast it as an advection problem. Which is described of a first order PDE. So how would that look like? Advection can be written such that we have the time derivative of a quantity, let's Q, call it Q, x of t, plus a times the derivative of that quantity equal to 0. That would be an advection equation, where Q, for example, that would be our quantity that we are interested in. And we mentioned it last time as well. Finite volume methods were motivated by conservation laws. For example, this could be a quantity which we want to be conserved. And then A here in this advection equation, A is the so-called transport velocity. So it's how fast the quantity is going to be advected. So let's quickly write down the wave equation in a form which resembles this advection problem. And so you saw that before. We can write the wave equation as well as a first order PDE. So that is the wave equation written in a velocity stress formulation. Would be the density times the derivative of velocity. It's equal to partial derivative with respect to space of the stress sigma. And then the coupled equation is the time derivative of the stress now becomes shear modulate times the derivative of the velocity. So this is the velocity stress formulation, and you see these are only first order derivatives, that system. So how could we cast this into the above form about advections? So let's rewrite it a bit in an advection form. Well, we would have first the time derivative of a quantity, which is here the velocity. Then the transport advection term, in this case would be 1 over rho with the derivative of the stress is equal to 0. So that will be the first equation that we will put into this advection form. And the same for the second one with stress. We have minus u derivative v is equal to 0. And so we can put these two equations together, but just using a vector q, let's call it capital Q, which is a vector with the velocity and the stress. And our matrix A, which we can write in this form. Then the above system becomes simply the following equation, where we have time derivative of Q plus A times the derivative with respect to space of Q is equal to 0. So see, this is in this advection form that we had above. But still, it's a coupled system of equation. So equation 1 and 2 here, they're still coupled. They depend on each other. So in order to solve it with the finite volume method, then the approach is basically decouple the system, which means we need to find a diagonal form of A. Then we have the two systems decoupled, two equations, and then would apply basically the same discretization approach like for an advection problem. So that's the approach basically in Hannah Eagle's book and Randall Levesque's book, how they solve then the wave equation. Put it into this first order system, PDE system. And now basically, so one would diagonalize this matrix A. How could you do that? Well, you would use its eigenvalues and eigenvectors. And the eigenvalues of this matrix A would be lambda 1 and 2. They would be plus and minus mu over rho. Those would be the two eigenvalues of that matrix A. And then you would take the associated eigenvectors to decouple the system. Before applying the finite volume discretization. Good. For us, basically, it's just to highlight how one approach using the finite volume method would look like for the wave equation. And so for more details, you can look at, for example, Heiner Eagle's book. That's Computational Seismology. You have that as well for this class. And then you would look at chapter 8, which describes the finite volume approach. Let me just mention 2 points here for the approach that he's doing then for the wave equation. We saw, for example, these upwinding schemes that you could use to interpolate the fluxes at the self faces. Unfortunately, upwinding is not very accurate and not that well suited for the wave equation problem. So what he will introduce is a so-called Lax-Vandroff scheme. For the advection problem. And this one is then second order accurate and better suited for wave problems. So it's again another interpolation scheme that you can use, especially for solving the wave equation. And then there is still an issue with having the possibility of having a discrete solution. So the quantity Q for the advection problem here, it could still have a jump, for example, from one cell to another. It could have a discontinuity that we want to advect. And for such discontinuous fields, one way to solve these is discontinuous fields. They would be solved by looking at the so-called Riemann problem. The Riemann problem deals with having this jump of the quantity from one cell to another. So that's what you would find, for example, in Heiner's book described, and also in Randall Levesque's book, which he refers to as well. So we can put this as an advection problem and then use basically the approaches for advections, how to solve those problems with a finite volume approach. Right. So the second, let's say a more naive approach I will show you now, where we just use our initial strong form and put this into an integral form. So we use the second order formulation of the wave equation. And now let's see how that would look like if we just put this into an integral form and then use finite volume approximations to discretize it. Good so far? Good. So for this first order system, I refer you to look at Heiner's book, for example, if you want to see the details about it. So let's start here with an alternative approach. Maybe a bit a naive approach. We use the second order formulation. Of the wave equation. Directly. To solve the following integral form. So we integrate over the physical domain omega. The left-hand side term where we have the density times the acceleration equal to the integral form of the right-hand side term. We have the divergence of the stress, which we write in 1D in this form here. Right, so this is the integral form of the strong form we had above. And the goal is we want to have this in a matrix form, so which we will put into a matrix form where we could write the mass matrix times the acceleration, which is a vector then, is equal to the stiffness matrix K times the displacement vector. So let's find out how we can construct these mass matrices and stiffness matrices. Good. So that deals with the discretization of the problem, of the equation above. So the first thing we have to do is we take the domain omega, the physical domain, and discretize it into a number of elements or grid cells. So omega becomes this union of the grid cells omega E. And we apply Gauss theorem, which is one of the fundamental ingredients of the finite volume approach. So this leads to the following equation. For each grid cell, we have then the integral over the grid cell, the density times the acceleration is now equal to the surface integral over E of shear moduli times the derivative of the displacement times the normal at that surface and integrated over the surface. So think of having a cell where we have the boundaries xa and xa plus 1 and the centroid, let's say at xp. So then we can write these integrals as an integral from xa to xa plus 1 of rho times the derivative of displacement dx is equal to mu times the derivative of displacement evaluated at these boundaries. Which is just these terms s at xa plus 1 minus the term at xa. So this here is going to be our mass term, and this thing here is going to be our stiffness term. So let's look at these terms one by one. And we'll start with the mass term here. So we have this integral from xa to xa plus 1 of rho times the acceleration dx. So this we can approximate with the finite volume approach, having rho at the centroid position xp times the acceleration evaluated at the centroid times the volume of that cell. Let's call it VE. So that would just be the finite volume approximation. You can think of having this grid cell with the centroid position xp, and then here we have the density rho p and the acceleration sp at time t. Is this clear, this finite volume approximation of the integral? We use now the centroid position values. Good. So how about the stiffness term? Well, here we have the shear moduli times the derivative of the displacement evaluated at xa and xa plus 1. So that's just a little bit more explicit, written out this difference between these two terms. And here again, we can just approximate this with the central difference approximation we saw from last time, where we have mu evaluated at xa plus 1, and then we have the central difference scheme sp plus 1 from the neighbor minus the value at the centroid divided by the difference to the neighboring centroid, and then xa times the same for the other boundary where we have the neighbor p minus 1, and the difference would be delta minus. So if you want to put this as a figure, we have here our reference cell with xp, xa and xa plus 1. And then we have that neighbor cell with the center at p plus 1 and one with the neighbor at p minus 1. So the distances between centroid here, which is called delta plus and delta minus. And then you see we approximate these derivatives of the displacement. Let's say by the central differences. And that gives us then these derivatives of S, the displacement evaluated here at a plus 1 position. And the same on the other side, where we have the derivative of S evaluated at position xa. So the naive approach here works if we assume that the displacement S is kind of a smooth function. So this approximation here is by central differences. Assuming that we don't have a jump of the derivative of S. So if S is smooth, then yes, this approximation should be right, should hold. So it's different to the above problem where we had the advection, where if you allow for a jump of the quantity, then we need to look into solving it with a Riemann problem. Where here we assume that we have a smooth solution field S displacement. And then we can make these approximations of the derivatives at the boundaries. Is it clear so far? So in principle, we are already done with the formulation, with the discretized formulation. We have the mass term and the stiffness term now discretized using a finite volume approach. Let me quickly note, put down a note about the material properties that we will need. So, quick question, what about material properties that we need to have? We had rho evaluated at xp from the mass term. And then we have the shear moduli at xa and xa plus 1. So the shear moduli here is needed at the cell faces, where the density is needed at the centroid position. So if we have our cell with xa and xa plus 1, the cell face, and the centroid at xp, then here we would have rho p needed, and on the boundary we would have the shear moduli needed. So let's quickly put that down. So U shear moduli is needed at the cell faces. Rather than at the centroid location. As rho is. So to make life a bit simple, so we can assume that also these material properties are piecewise linear. So assuming they are piecewise linear, we have two options basically. We can either define the we can define them at the centroid position together with the gradient. At centroid positions, together with the gradient information. Or, which is probably simpler, we specify them, or simply specify them at the cell boundaries or cell faces. At cell face positions. Directly. And you see, this is similar to, for example, a staggered grid approach with finite differences. So finite volume methods, the discretized way, often is either identical or very similar to a staggered grid finite difference scheme. So for simple homogeneous cases, you can show that they are actually related to each other. Staggered grid finite differences approaches. Well, for density, so we do need density at the centroid position, xp. So if we have density given at the cell faces, we still have to figure out what the position would be at the centroid position. So let's say we have rho at A and A plus 1. Then obviously the centroid position that we want is the average value of rho within that cell. So rho xp should be the average value, which mathematical terms would be like the density integrated over the cell. Which, just for this simple 1D example, is just the average of the two cell face values. So it's just rho A plus density at A plus 1 divided by 2. That means we can define the shear moduli and the density all at the cell face positions. But then we actually use the interpolated value for the centroid position for density. Also, a short remark, these material properties, they don't have to be continuous across elements, but they can have
Professor,
a jump. Yeah?
I just received a message from Tariq. He
Mm-hmm.
cannot log in into the class.
Good, we have both Inra and Tariq.
Okay.
Good, hello Indra.
Hello, Professor.
And Tariq, you're online as well?
Yes.
Good, great. Now you're logged in. So let me quickly finish this note about the material properties. The shear moduli mu and density rho. So they can be defined at an elemental which we sometimes call local level. And so this is similar to the finite element approaches that we saw. So it's similar to finite element and also the spectral element approach. We can define the material properties for each cell, and they allow for jumps. Good. So Tariq and Indra, what we started with is the wave equation problem. And then the goal is to solve this with the finite volume approach. So the first step that we need to look into is the integral form. And then there is one way of approaching it is by casting the wave equation into an advection problem. You see here on top is the advection equation. And so we can write the wave equation as a velocity stress formulation, where we only have first order derivatives, and put this into an advection form, and then solve basically the advection problem with a finite volume approach. And this way is done, for example, in Heiner Eagle's book, and also in Randall Levesque's book, which he refers to. So now it's basically the same machinery that has been developed for advection problems can be applied to the wave equation problem. There are two two points which you have to be careful about. One is the advection problems, they should be decoupled, whereas if you write down the wave equation, it's basically a coupled system. The two equations are coupled between velocity and stress. So in order to decouple it, you would look into how to diagonalize this A matrix here. And for that, you would need to find its eigenvalues and eigenvectors. But then you basically have these two equations decoupled. Now you can solve it with the typical finite volume approach for advection problems. The other point is that when you do the advection problem, the finite volume method is basically motivated to do this as well for discontinuous solutions. So you can have jumps in your quantity that you advect. When you have these jumps in your field, then what you run into is a Riemann problem, where you have from one cell to the other a sudden jump of this quantity. Then you need to be careful about how to solve this Riemann problem on the cell boundaries, for example. But this can be done for the wave equation, and then you basically find solutions to the wave equation based on solving an advection problem. And so this you would do, for example, if you would have shock waves, nonlinear wave phenomena. Then you would cast it into this sort of form, advection form, solve the Riemann problem, and you could solve this for nonlinear wave behaviors. Now, the alternative approach that we use here is a more naive approach, a simpler approach, where we just start with the second order formulation of the wave equation. And now just write down the integral form and then discretize it and approach it with a finite volume approach like we saw last time. And we looked at the Poisson equation. So we can approximate these integrals, where we have a mass term and a stiffness term. Both we can approximate with a finite volume approach. And here we basically assume that the solution field, so the displacement S, is smooth. We don't have a jump in between, so that the derivative can simply be approximated by these central difference schemes. the same schemes that we saw last time for the Poisson equation. So it's a simpler way of approaching the problem. And then basically what you have to look into is where do we need the material properties. For the mass term, we need it at the centroid position. Where for the stiffness term, we would need these at the cell face positions, or the face centroid positions. So if we just assume that these are at least piecewise linear properties, means that we can just define them at the cell face positions, centroid positions of the faces, rather than at the centroid position where we would need also a gradient information. So it's a bit a simpler approach, but this is also related to these staggered grid formulations. So you have the similar issue of where you define the material properties. Good, and again, the material properties, they are allowed to be discontinuous with the finite volume approach. So we can define them on an elemental level rather than on a global level. Good, so let me write down the discretized equation, like for this we had above here. So the integral form discretized will then just look like this. So the discretized equation looks like the density at the centroid position times the acceleration of S at the centroid position times the volume is then equal to the shear moduli at xa plus 1 times our approach, the derivatives, delta plus minus mu dxa, this approach p minus 1 delta minus, right. So let's use the average here for the density on the left hand side. Put this together with the volume of the cell. So then we have rho A plus 1 divided by 2, that's the average value, times the acceleration at centroid position P for time t, equal to, now let's separate these terms for the displacements. We had displacement at centroid position P plus 1 minus these terms for the centroid position at P plus this term for the centroid position P minus 1 t. So now you see how we can cast this into a matrix form where we then have the coefficients of the mass matrix times the acceleration. And here this can be cast into this stiffness matrix times the displacement. Right. So how do we do the time stepping? Let's just use the same Newmark scheme like we had, for example, for the spectral element approach. So using the Newmark scheme for time stepping, will look like this, where we have this predictor step of the displacement. So we have velocity plus a term with acceleration. The velocity predicted time n+1. And then the acceleration is put to 0. Then we have the solver step. We can just write the acceleration is now the inverted mass matrix times the right-hand side vector f, which we can just write in terms of the stiffness matrix applied to dn+1. And then we have this final correction step where we correct the velocity using this updated acceleration field. Right. Okay so far? So you see we have the matrix form, the discretized equation. Then we can use that to solve for the acceleration within this Newmark time scheme. So the last ingredient we still need is for the boundary conditions. Let's quickly put those together as well. And then we are all set to solve the wave equation with this finite volume approach. So let's start with the Newman boundary. So slightly simpler. So we have, let's say, the boundary at 0 and L will both vanish. So at the left, we have this term here to be 0, which basically means our surface integral for that grid cell, the boundary. Can write it in this way. Will become just u at xa+1 s at xa+1 t minus now the Newman boundary, which is 0. So this one we can just then write in this discretized way. With these two terms. Right. So this XA, that's where we impose what the derivative is directly with the Newman boundary. So the only term that we are left with is the one on the position A plus 1. And this we just approximate again with the neighboring centroid position. Good. Similar for the right side. We have the derivative at L. It's going to be 0. So that means for our grid cell at that right boundary, we can approximate this as just the second term for the derivative. Oops. And then write this again with these terms with UA. Centroid position P plus UA delta minus at centroid position P minus 1. Good. These would be the modification for the Newman boundary. Let's also look at the Dirichlet boundary modifications. The Dirichlet boundary, where we have the displacement imposed at the boundaries. So how would the left-hand side look like? Well, we impose here as at position 0, which basically means that for our grid cell here, we have the displacement at the centroid position P and the displacement at the boundary, let's say x0. But what we need is the derivative at the boundary at x0. So again, in this case, we can just use a simple backward difference approximation for the boundary. So what we need is the stiffness term for that grid cell. Well, we have both basically the derivatives at A plus 1 minus the derivatives at A. And so this one here is now the tricky part. That's the one which involves now the Dirichlet condition. And so if we want to approximate that, so that's the position at x0 and the derivative at x0. How would we approximate that? Well, we can use this simple backward difference scheme. So then this term here is going to be approximated by mu at x0. And then we have s at xp minus s at x0 divided by the distance between these 2 points. And now we can just cancel out this displacement value at x0. That's the boundary condition. So what we are left with is basically the first term for SP minus 0. So now we impose this Dirichlet boundary for that derivative. This is a simple first order approach, but it will do for our example. So the whole grid cell, you see, then the modification for the full grid cell will be the usual derivative at a plus 1. Now with this modified term at the Dirichlet boundary, so we just have this UA over the delta x0 SP T. So we can put this together so that it's very easy to see what the coefficients would be for our stiffness matrix. Good. And so let's finish with the right side, where we have L, displacement imposed. So here again, similar approach. We would have, let's say, xn, and then here xa, or n minus 1. We have the displacement at the centroid and also the displacement at the boundary that we're going to impose here. So again, then we can approximate this derivative by this sort of backward differencing. So in this case, the term that would be at xa plus 1 involves the boundary displacement. Which is just this backward difference approximation. Which then we can write at this in an explicit way. U at, that would be n, position xn, minus this difference SP times T. And so the full grid cell would look something like that. We would have now this modified boundary term minus now the standard approach for the derivative at the opposite point, just XA, using the centroid position, neighboring centroid position P minus 1, which we have available. So again, putting this together makes it very easy then to see what the stiffness term element will look like. And P minus 1 T. So these are the modifications that we would need to apply to the stiffness matrix. Right, so when you compare Newman condition and Dirichlet conditions in a finite volume approach, you see that the Newman conditions, they can be applied exactly, whereas the Dirichlet condition has to be imposed by, in this case, just a first order approximation. So it's similar like the finite element approaches. The Newman boundary conditions become easier to apply than the Dirichlet boundary conditions. That's just a final note here that the Dirichlet boundary only uses a first order approach here. To impose it here. Whereas the Newman boundary is exact. Good, with that we're all done. We're all set to use the finite volume approach for the wave equation. So I will put you the homework folder with the template Python script again on GitHub. Then you can see if you can solve it and play a bit around with the finite volume approach. For example, see what's happening if we do have a jump in the material properties. And then probably you want to compare this solution, the finite volume solution, against the spectral element solution that we already implemented before. So then you can compare this low order versus a high order scheme, for example.